Thank you very much for attending my presentation. My name is Matthieu Parenteau, and today I will be talking about the development of parallel CFD application using the Chapel programming language. And so we'll start with a brief introduction of the Chapel programming language, and then we'll talk a little bit about the CHAMPS, which is our 3D unstructured round flow solver that we've developed. And then we'll present some scalability analysis that we did of CHAMPS. And then we'll present some numerical verification of the various models implemented in CHAMPS. And this will conclude the presentation. And so what is Chapel? So Chapel is a modern parallel programming language. It is portable, scalable, open source, and collaborative. So it's originally developed by Cray, which is now part of HPE. And the main goals of Chapel is to support general parallel programming, but more importantly, to make parallel programming at scale far more productive. And now, why consider a new language? Well, first, to improve the programmer productivity, and at the same time, to get as much performance as we get from optimizations from the compiler. And then finally, the language defines directly what is, whether it's easy or hard to implement a particular algorithm. And so it influences the algorithmic thinking behind. And so just to sum up Chapel, and so it aims to be as programmable as Python, fast as Fortran, scalable as MPI, portable as C, and flexible as C++. And in order to show some key feature of Chapel, here I'm using just a very simple benchmark test called a stream Triad. And so here we are simply adding a vector to another one that's been multiplied by a scalar. And so first, Chapel uses the concept of locale, and you can think of locale as a compute node. And so here in the figure in the top right, you can see that we have a vector A, B, and C that are distributed on the available compute nodes, which is divided by the red lines. And on each of those compute nodes or locale, we have a number of cores, which are represented by the blue line. And Chapel can use that local parallelism as well to perform any type of computation. And so in the end, in just 13 lines of codes, using the DMAP and the block distribution feature, we can have any array distributed on the available compute nodes and then perform in parallel the required computation. And so at the bottom right here, we are just showing a simple graph comparing the performance of Chapel compared to an equivalent implementation using MPI and OpenMP for this stream Triad benchmark. And as you can see, the performance achieved by Chapel is very similar to that of MPI and OpenMP, even at 256 compute nodes or locales. Now, as you can see, Chapel has many interesting features for CFD. The first one is being productivity. The second one is providing fast software that are necessary since CFD incurs very high computational costs. And last but not least, it's portable and scalable application because we want to be capable of applying application from a single desktop to a large case 3D cases over any distributed systems. And so since Chapel has all these interesting features, we decided to try it and for a real CFD application. And so we've decided to build a 3D unstructured round flow solver entirely with the Chapel. And we name that software CHAMPS for Chapel Multiphysics Simulation. And so here I'm listing the various algorithms and models implemented in CHAMPS. And for the various results presented in the paper, we are using the second order finite volume scheme with the row upwind scheme for the convective flux. And we are using the Spalaro-Maurras turbulence model and the SGS implicit solver as well. Now, since when we've developed CHAMPS, we wanted to have the capability of performing a multi-physics simulation. And so this requires different computational grids. And so we needed to have a very flexible structure. And fortunately, Chapel provides a similar feature than C++ that gives us that flexibility. And so the way it's implemented, it's using inheritance and type aliases. And so we have one global object here called global handle. And the functionality of this object is to distribute any kind of computational domain over the available compute nodes. And so here, afterward, we have different computational domains that are implemented using inheritance. And so that allows us at the same time to be able to compute the flow solution along with the droplet solution that requires different computational domains. And for the parallelism over distributed memory, there's one really big difference when compared to an equivalent MPI code, is that with Chapel, the code is executed only once. And when we execute the code, we are we give as an input the number of locale or compute node. And then inside the code, using call-for-all statements, we are creating all the necessary tasks. So we start first by creating a task for each locale, and then each of those tasks on each locale will create a task for every core that is available on that locale. And then we have the long nonlinear iterative process that starts afterward. And so this is an efficient implementation, since we are only creating the task once at the beginning of the solver. And so obviously all those tasks need to be synchronized together. And this is where we use interface. And so the zone is partitioned into a defined number of zones. Normally it's one zone per core. And so we are using here dedicated arrays of buffer for read and write. And so basically we will have every zone fill the buffer with the required values to exchange to the other zone across the interface. And then once every buffer is ready, we perform the exchange. And since Chapel supports global namespace, here every locale, every task has access to the buffer, even if it's located on a different compute node. And so this is done very efficiently. Now, for the scalability test, we have been using a Cartesian grid. It's a simple cube with only far-field boundary conditions. And we've done a strong scaling and a weak scaling analysis. For the strong scaling, the cube is discretized with 800 elements in every direction for a total of 512 million elements. And for the weak scaling, the problem size is scaled with the number of locales. And we try to maintain approximately 1 million cells per locale. And so here on the left, we are presenting the strong scaling results, and on the right, the weak scaling results. And we've realized that the global reduction that we are performing at every iteration is highly impacting the scaling results. And those global reductions are just reduction on certain values to monitor the flow convergence. And so this is the reason why we are presenting results with and without those reductions. So the red lines are the results without reductions. And you can see on the strong scaling over here that without this reduction, we are maintaining linear scalability even at 256 compute nodes. And for the weak scaling, you can see that without this reduction, the red curve is much more closer to the ideal one over here. And so this just indicates that our implementation of global reduction is not efficient and needs a little bit more work. Now, for the numerical verification, here I'll just be presenting a few. For more details and more cases, there's more details and more cases in the paper. And so here it's the flat plate turbulence model verification. We are for the Spalamas and K omega models. And as you can see, the CHEMS results are in red, and we are very consistent with the literature. We also did the 5th drag prediction workshop. And so again, here the results of CHEMS are in red. On the left, we are showing the angle of attack convergence for a lift coefficient of 0.5. And on the right is the total drag coefficient. And as you can see, in overall, we are consistent with the other participants with a drag coefficient slightly higher. And here on the left, we are presenting the pressure drag coefficient, and on the right, the friction drag. And so as you can see, in general, we are consistent with the participant results. Now, to conclude, the development of distributed memory application is very efficient with Chapel. In our experience, we've experienced at least 2 to 5 times faster implementation times with Chapel than with C and C++. And in terms of performance, we're very pleased because we're seeing performance that are very similar to equivalent C and C++ applications. And in terms of scalability, as you saw, without the reduction, is very good. And so future work will involve adding more complexity. And so a fluid structure interface for elasticity for example. And so I'd like to acknowledge the great support from the Chapel team at HPE, and also the support from our other contributors for the resources that were required for this research. Thank you very much.